Good evening, and thank you everyone for coming out tonight. On behalf of the Lenape Regional High School District and the Board of Education, I would like to welcome several special people with us this evening, and I will ask that you hold your applause until the end. Tonight we have two of our Board of Education members with us, Bonnie Alt and Barry Fitzgerald. We also have our Superintendent, Dr. Carol Birnbaum, Principal, your Principal, Donna Charlesworth, Supervisor of Business Technology, Health and PE, Michael Carr, and our Project Lead the Way teachers, Carl Kralik, Nate Knaus, Michael Robinson, and Jeff Thompson. We would like to thank our sponsors also who have generously donated to the Project Lead the Way program throughout the Lenape Regional High School District, and they are Lockheed Martin and BAE Systems. Tonight is a monumental occasion for these students, as this is the culmination of 4 years together as one cohort of students, as the first Project Lead the Way students to complete the 4-year program at Cherokee, which will pave the way for all those who come behind and all the future students. They began this journey together as freshmen, probably not knowing exactly what would lie ahead, and here they are now, 4 years later, ready to show their family and their friends what they have been working on for the past year. So students, congratulations. We're excited to hear from you and see your designs in action. And next, it is my pleasure to welcome Mr. Nate Knaus. Thank you.
Thank you, Mrs. Zanakis. Good evening, everyone. My name is Nathan Knaus, and I've had the pleasure of teaching this year's Engineering Design and Development class. Engineering Design and Development is the fourth course in a sequence of courses which intend to show students the roles engineers play in our society by discovering new career paths and possibilities and developing engineering knowledge and skills. Through their 4 years in this program, our students worked in teams to design and test solutions to a variety of problems in many different engineering disciplines. Through these courses led by Mr. Kralik, Mr. Robinson, Mr. Thompson, and I, students picked up skills that can be used in an engineering program, but also developed in-demand transferable skills like teamwork, collaboration, critical thinking, and many other methods of technical and verbal communication that'll make them strong leaders in any industry that they choose. This year, the knowledge and skills students acquired since their time as freshmen came together in EDD as they formed teams to identify an issue which led them to research, design, and test a solution, ultimately presenting their solution to a panel of engineers and all of you here tonight. Tonight, you will hear about the problems that they've identified and why the problem is in fact a problem. You will also hear about the current methods and actions that don't completely solve those problems, as well as the product development and testing that our students were able to complete throughout the course of this year. As I mentioned earlier, our students have been receiving feedback from a panel of engineers and STEM professionals throughout the course of this year. Tonight, our panel of professionals consist of the volunteers from local businesses and the community who attended our preliminary and critical design reviews. These individuals took time out of their busy schedules to provide feedback and advice to our students throughout the course of the year. And I'd like to call your attention to the back of your program where you can see a list of this year's volunteers and the companies and organizations that they represent. At this time, I'd like to thank them for their efforts and their commitment to our students. So thank you guys for helping out this year. Appreciate it. All right. So now it's time to begin our presentations. With that, I'd like to invite up Paul Durante, Nick Mascallo, and Kiefer Montanaro up to the stage, and we'll all learn together about the smart bin. All right, here they come.
So I'm Kiefer Montanaro.
I'm Paul Durante.
And I'm Nick Mascolo, and our project is the Smart Bin, our solution to recycling contamination. Our problem statement is that ever since single-stream recycling started back in the 1990s, Effective recycling has been almost impossible for businesses due to recycling contamination. 1 in 4 items placed in recycling containers are not able to be recycled. This is the central problem facing the advancement of recycling because the non-recyclables dilute material quality, reduce value, and damage the recycling infrastructure. Even if the load is sent to a recycling facility, the inappropriate items still damage the machinery, contaminate otherwise valuable material, and even endanger workers. So back in the beginning of the year, when we were brainstorming problems we would like to solve, I was inspired by my part-time job. While collecting trash, I realized that when customers are given both a trash can and a recycling bin, most still throw away a lot of trash in the recycling bins. And this constant contamination resulted in the recycling company refusing to collect from us. So our goal was to create our own recycling bin that would separate trash from recycling before the two were able to be mixed and contaminated. When trying to justify our problem, we ran into 3 main issues. Recycling contamination is bad for the environment because natural resources are depleted and more waste is sent to landfills. It is also bad for the economy. The National Waste and Recycling Association found that recycling contamination cost the city of Phoenix, Arizona, $722,000 in 2009. Recycling contamination is also dangerous for workers because when contaminants break the sorting machinery in waste management facilities, the repair can be very unsafe. Through our research, we found 3 products that aim to reduce recycling contamination. However, we discovered that the affordable solutions were often very ineffective, and all the effective solutions were very impractical to be purchased by businesses due to their expense. So our goal was to create a product that would work and be affordable for businesses to use.
Okay, so our requirements were that the solution must keep recyclables separate from any other waste. It must be safe to use. The material cost for the solution must be under $350. The solution must be entirely waterproof. It must be easily movable, and maintenance must be easy. Our design work. These were Kiefer's brainstorms, Nick's brainstorms, and then my brainstorms. And then from these brainstorms, we collaborated and made 3 final brainstorms of what we thought we should move on with. Now, using those brainstorms, we put them against each other using the criteria listed above, using a decision matrix, and from the decision matrix, we came to the conclusion that Nick's design was the best, having the highest score of 67.
So here's our final design. Right here is a picture that annotated the many features of our product, and it works like this. The user will open the lid and drop their item into the holding area. And then once the lid is closed and the latch is locked, the item is then released into the detection area, where cameras determine whether the item is trash or recyclable, and then from there it is sent to its appropriate collection bin. So from there, each of us divided the product into 3 separate subsystems.
All right, so my subsystem was the general structure. So I decided that the frame would be made out of PVC pipe because of how light it is and how strong it is. We decided on the dimensions to be 2 feet by 4 feet by 2 feet.
My subsystem was the lid system. I had a rectangular lid, a latch, 2 servos, and then those would release the item into the detection area.
I had the software subsystem, and I decided to use a Raspberry Pi camera module and a Raspberry Pi 3B Plus and image classification software to determine if items inserted into our device are recyclable or landfill. How will this software actually sort the items? Well, first the camera will take an image of the item. This image will be fed as input into a pre-trained image classification model, and the model will return a % value for each class. And based on this value, the item will be dropped into either bin. So for example, the device takes a picture of a water bottle. This picture is put through the neural network. It returns that it thinks it's 83% certain that it's recyclable, 17% certain it's landfill, so it would be dropped into the recyclable bin. I also did the control system subsystem. Like I said before, we're using a Raspberry Pi and a Raspberry Pi camera. but we're also using a rotating plate mounted on a stepper motor to drop the item into the correct bin once sorted. This stepper motor will receive 12 volts of power from the wall, and the Pi will also be powered from the wall, and the Pi itself will power the Raspberry Pi camera and the electronic latch using its GPIO pins, and it will control the motor and the camera with Python code. And here's our prototyping.
And here's my lid system prototype. So I have a rectangular lid, and the bump switch mimics the lid locking. And the ultrasonic sensor is a distance sensor, which determines if there is an item in the holding area. And then at the bottom, 2 servos, which turn to release the object into the detection area.
And I did the control systems prototype for the Nix lid system. This is some basic code written in C for the VEX module, and it pretty much just detects when the ultrasonic sensor value changes. And so that means when an item is over top of the ultrasonic sensor, the servos will rotate and drop the item into the next chamber.
We tested the holding area by placing different items of different shapes and sizes to determine if the detection process was effective. Each object had 3 trials and was graded on a pass-fail system, and any observations we had were recorded on the right. After our test, we found that curved objects were not being able to be detected properly due to redirecting sound waves. In order to accurately detect curved objects as well as clear objects, we combined the ultrasonic sensor with a light sensor that we placed at the bottom of the slabs. That we then performed the tests, and we determined that the detection process was 100% effective.
So our final structure design, we had to shorten the width from 4 feet to 3 feet because at 4 feet it was too hard to move around and it just took up too much space. And for the final lid design, we had to take several pieces of sheet plastic, put it together, and using hinges, we drilled it into the PVC pipe to attach it.
And here's the final training data. This is the final training program written in Python using TensorFlow and Keras libraries. It was trained on over 2,500 images from 6 different classes. The image sizes are each 224 by 224 pixels. And this model was trained over 10 epochs, which pretty much means the model was trained on all 2,500 images 10 times. It just helps the model recognize more patterns and obtain a better accuracy. Here's the training data used in that training program. The classes used were cardboard, glass, metal, paper, plastic, and trash. And like I said, there's 2,530 input images. Here's the testing input manipulation. This is for when the device is actually trying to classify an item when it's put into the device after the model's been trained. So first, the images are taken from the Raspberry Pi camera. They're resized to 224 by 224 pixels. The RGB values of each pixel are then divided by 255 to map the values between 0 and 1. This just makes it easier for the neural network to understand them. This 2D array of pixels is finally stretched into a 1D array. This is again to make it more readable for the neural network. And this 1D array is inputted into the neural network, into its first layer, and after going through convolution through multiple layers, an output is produced. So for example here, the Pi camera takes a picture of a banana. It's resized to the correct specifications. The RGB values are normalized between 0 and 1. It gets stretched into a 1D array of RGB values, and then the values are assigned to the input nodes of the model, the output nodes produce the results. In this case, node 2 was 90%, and node 1 was 10%, so node 2 would be the winner. And I also did the final control systems for our device. Obviously, we're using a Raspberry Pi and also a stepper motor, and I decided to use a button to simulate the lid closing. When in this Python program, it detects when the lid is closed, and when it detects that, the Raspberry Pi camera is triggered to take an image of the item. This image is then put through our neural network, which returns a result, and that result determines which way the stepper motor spins to drop the item into the correct bin. Moving forward, we hope to mount the rest of our electronics that we didn't have time to mount due to time constraints. We hope to implement our electromagnetic latch to our lid system to make it so no one can insert their hand into our device while it's processing an item. We hope to waterproof our device because as it stands, it's not very waterproof. Also improve the aesthetics of our device for obvious reasons. And we hope to spend more time debugging our convolutional neural network because we think with a little more time in development and a little more debugging, we can really get a working product. Thank you for your time.
Convolutional neural network. I don't know what that is. Good job, guys. All right, so our next group coming up here is a group looking at the wilderness checkpoint. And those members are Lauren Fowler, Palak Jain, and Harrison Olt. Come on out.
All right, good evening, everyone. I'm Harrison Ohl,
I'm Palak Jain.
And I'm Lauren Fowler.
and we are the Wilderness Checkpoint.
So throughout this year, we had to find a problem statement and find a problem that we wanted to solve. And our problem statement basically says that there are many times where hikers get lost in the woods and it's very difficult to find them. And we wanted to solve this problem by creating a device that could locate hikers in the woods and also kind of help them navigate their way through the park. So our justification for this problem, so hikers are obviously the ones who suffer most from this problem. They are the ones who get lost, and this can be very traumatic, can result in injury or death. And National Park Services also deal with this problem, and not only does it damage their park's reputation to have lost hikers, they also have to take time out of their day to deal with this problem when they could be doing more things to preserve the national parks. And emergency services spend a lot of time on lost hikers. Sometimes it can take 10 to 14 days to find one person. This costs a lot of money, costs a lot of time, and is ultimately can be avoided. And so we are focusing basically on the mainland United States and the national parks in this area. So we've asked a lot of different sources to see if this is an actual problem, and experts and online reports have both said that this is a problem, and national parks have told us that this is a problem. And basically, we've taken a survey on a hiking forum, and hikers have told us that they have had difficulty navigating through national parks, and they would invest in technology that helps them navigate as well as helps them call for help when they need it. And so we interviewed the head ranger at Sequoia and Kings Canyon National Park, Ned Kelleher, and he told us that this is something he deals with on a daily basis, and it does take time out of his day, and he needs a better solution to the problem because one doesn't exist yet.
So to further research our problem, we looked into prior solutions that already exist, and we found some common traits between them. So we found that they were all pretty much handheld mapping systems that could display a hiker's exact location using GPS. They could communicate to either a hiker's cell phone or email, and they always had an SOS function for emergency responders to come get them in the woods if there's a problem. So some advantages we found with these products is that they're highly portable for hikers to use. They use satellite positioning systems to find a hiker's exact location. They can send information via satellite to a hiker's phone or email address. And they have trails and topography on the map for hikers to use and stay safe. But some disadvantages we found with these products is that the battery life often isn't long enough for long hikes. They have wild expenses for the products and often have subscription fees to use all the different functions like communication and SOS. They easily suffer from weathering and damage, and they don't work in remote locations, which the company making them doesn't provide for. So we found that our product does have a gap in the market, and we'd like to create a new type of hiking GPS. We'd like to make one with location sharing with search and rescue teams and park rangers, so that if there is an emergency, a hiker can alert them and they can find their exact location immediately. And we'd also like to reduce the cost to make hiking GPSs available to more more hikers.
So next we made a list of design requirements for which our product has to follow. The most important ones were that the product must communicate location information to a hiker's cell phone or emergency services within 1 minute of the hiker sending the request. The product has to remain clean of dust or dirt. The outside of the device should be brightly colored. The product must use a material like a clear, durable plastic to protect it from falling, weather, or animal damage. The product must withstand outdoor conditions like rain, snow, or high winds. And the product must have a rechargeable battery that lasts between 16 and 25 hours. We also have more design requirements, but they're not as important to our product. Next, we each came up with a final concept of what we thought the product should include, and we shared them with each other to make a final design. So this is a picture of our final concept drawing, and we took the most important aspects from each of our design and incorporated them into this picture. So we thought that the device should be in trails like 1 to 2 miles apart so that as hikers are walking on trails, they can track themselves through the woods. We also wanted a QR code system so that each hiker would have a personalized QR code that they got from our website that we made, and that as the hikers walk through the trail, they could check in their QR code to the device so that they could be tracked throughout the trail. And lastly, we wanted to have an SOS button so that the hikers could contact emergency services in case of an emergency. So the picture to the left shows our final design. It has a screen, a SOS button, a scan button to scan the QR code, and a power button. So for the prototype for the structure, I made a 3D model to show that the components fit inside the box and the box can be sealed. The image shows the 3D model and how all the parts fit inside.
So for the prototypes for the electronics, which is the hardware of the device, I created 2 different circuits. The first circuit was a solar panel battery circuit to test that we could power the device in the woods. And the second circuit was the Raspberry Pi circuit, which had the camera, the display screen, and the computer module, which would perform all the functions of the device.
So for the coding prototype, there were a couple of things we had to do. The first was coding the camera so that it was able to record and focus on images and put those images back onto the screen. The second was we needed the camera to recognize and extract information from QR codes. And the third was that we needed to code the Raspberry Pi so that it could support all of these functions. We did run into technical difficulties with the camera, the Raspberry Pi, and the SD card, but working through those technical difficulties was a really good learning experience.
Then we had to test the product. So the testing for the structure was I had to test the components, and I did this with a 3D model. Then I had to test to make sure that the product was waterproof, and I did this with a spray test. So I put a dry paper towel inside the box and then closed it and sprayed it, and if any water got inside, it would show that it's not waterproof. We also had to test the appearance and the symbols to make sure that the product was bright enough and that the symbols were clear, and we did this with a focus group which consisted of a few of our classmates. And lastly, we had to test the durability, and we did this with a drop test. So the results for the testing was that the 3D model showed that the components fit inside the box and it could be sealed. For the waterproofing test, we had holes in the box from the screen and the buttons. So even though the box was already waterproof, the holes made it seem that it wasn't. So we sealed the holes with sealant putty, which kept the water out after our tests. For the appearance and the symbols, we walked a certain amount of distance away and asked their classmates if they could see the box, and it could be seen from about 50 feet away, which is a pretty good distance. And we asked them if our symbols were clear enough for them to understand what they were, and they said that it was. And lastly, we dropped the box from about 5 feet, which is where it would stand on a post, and it was able to withstand this drop, so it passed the durability test.
So for the testing plan for the electronics, I created 3 different tests. The light condition test is to test that the solar panels provide enough power for the device while in the woods. The battery power test is to make sure that the solar panel battery circuit provides enough power for all the components to run. And the solar panel power supply test, that tests to see how fast power is produced by the solar panels. So on your left is the solar panel battery circuit that I created, and on your right is the Raspberry Pi circuit with the camera and display screen attached to it. So the results of the light condition test, we found that the solar panels we're using provide about 1.9 volts in good conditions, and this means that we would need 4 panels to power a device. The results of the power supply test, we found that with the solar panels, we could hypothetically power a device using the tolerances of the components with the manufactured labels, but we never got to perform the power storage test due to time.
So for the coding, we had to do about 4 tests. The first one was the screen test. We had to make sure that the screen was able to connect to the Raspberry Pi and display the Raspberry Pi interface. The second test was the camera module test, and we had to make sure that the camera could record and display that image back onto the screen. The third test was the SD card test, and we needed to make sure that the Raspberry Pi could extract information from the SD card and display the official Raspberry Pi program. And the fourth test was our website test to make sure that the website was easy to read and clear to any hikers who might use it. So this is our website that we created. And in this website, there is a list of directions as well as images to show hikers how to use the website. And there's a link that takes you to a QR code maker. And once you enter your personalized information in, it creates a personalized QR code, which is then printable. So these are pictures of our screen. So this is the official Raspberry Pi interface. And this is the code we used for the camera. And this video basically shows how the camera displays the image onto the screen of the QR code. And because of this, hikers, once we added code to read the QR codes, hikers would be able to check in with their QR codes. And this is basically our setup. And inside the box, we had a lot of electronics. And these are the different ports that we used in those electronics. And we also had buttons. We had an SOS button, a scanning button, and a power button.
So the next steps that we would take to finish our product would be to finalize the SOS function using the radio transmitter and receiver so that we could send the SOS signal beyond the device. We'd like to mount our device to a post, which is how it would be along hiking trails on national parks. We'd like to add hiking trail data to the screen so that hikers could view it from the device. We'd like to integrate our button circuit so that the buttons have the proper functions. And finally, we download Raspberry Pi program that could recognize unique QR codes for each hiker. Thank you guys very much.
All right, thanks guys. All right, I'm sure a few of us have been in that scenario and could definitely benefit from that product, so thank you. All right, so next up, if you are a fan of 3D printing, you'll appreciate this. We're gonna learn about recycling 3D printing filament, and the 2 people taking care of that are Michael Kurtz and Andrew Palmer. So come on out, guys.
Hi everyone, I'm Mike Kurtz,
And I'm Andrew Palmer.
and this is our project, recycling 3D printer filament. So here's our problem statement. The most significant issue with the 3D printing industry is the one-time usage of filament. Companies that use 3D printers annually on a daily basis, they have no use for their waste filament, which can total up to 600 pounds a year. Over 90% of consumers believe that this is a problem, and over 100 million pounds of plastic each year are used to create filament. Most filament, ABS and PLA, the 2 most common types, they do not decompose quickly and they are harmful to the environment. So to validate this problem, we conducted a survey. Out of 24 people surveyed, about 92% of them believed in making a solution to this problem, and they would all pay $100 to $200 for a solution. We contacted a 3D printing expert on the issue named Grant Posner, who runs his own 3D printing business, who also verified that yes, this is indeed a problem and there is no perfect solution as of the moment.
Next, we researched the previous solutions. The previous solutions we found are the Protocycler, Filabot, Cal Berkeley solution, Philostruder, and the option of buying new filament. The issues with these solutions are that they're either too expensive or not available on the market. For example, like the cheapest, well, least expensive solution is the Philostruder, and that still costs over $100, more than what people are willing to buy. And like the more expensive solutions, they could cost like in the thousands. Also, the Cal Berkeley solution is not available on the market. They made it for the school itself, so no one could really buy it. We plan to address these issues very clearly. Our solution will cost under $200, which is within the price range of what people are willing to buy. It's also the same price of 3 spools of filament, and it's like half the price of anything else. We also plan to put this solution on the market in the future.
So next we talk about our final brainstorm. So it consists of 3 subsystems all mounted together on a wooden board. The grinder is a coffee grinder that will, you put plastic into it, you grind it up for a few seconds, and it turns the plastic into little dust-like bits. The melter melts all the bits, and they get transported to the extruder at the very end, where they're extruded into a new constant line of filament.
Next is our prototype construction. We made a list of parts in order to help us buy what we need to construct our device. We would use a small black coffee grinder as the base of our grinding system. Then we'd use a PID temperature controller, a single state relay, and a heating band to construct our heating system. Now when the filament is poured into the heating system, it's also connected to like this weird extruding screw. That would be created from an auger drill bit, a steel pipe with a hole in it, and a brass end cap. Well, that would be powered by a motor.
So here's our collection plan. We created a Gantt chart in order to streamline our testing process and keep us organized on top of dates, and here's a compressed version of it. So we gathered a whole lot of information from testing, or the information we wanted to gather from testing was that we made tests for each of our subsystems in order to determine if they were successful or not. So we wanted our machine to grind filament effectively. We wanted it to maintain a constant heat, constant temperature while melting the filament, and then extrude it at a constant predetermined rate so that it wouldn't get baggy or the diameter would stay constant during the creation process. So the grinding device test. Filament is put into the grinder for about 20 seconds, and you hold down the power button as it gets shredded into little bits. So the way we judge this test, whether it worked or not, we took the smallest bit of filament, or the largest bit rather, and if the radius of the chunk was under 3 millimeters, then we concluded that the test was a success, and it had to be 85% efficient. That is, 85% of the particles had to have a diameter of less than 3 millimeters in order for the test to pass. Yeah. The heating device test, we had a heating band held up in the air by metal suspenders by helping hands, wired up to the temperature controller and the thermocouples. We had an electronic temperature probe attached to the ring at all times, which constantly monitored the temperature and told the temperature controller it needs to be hotter or less hot, and change the temperature accordingly. So in order to pass, the actual temperature of the device could not fluctuate any more than 5 degrees Celsius up or down. As for the extruding device test, the auger drill bit is attached to an extruder, an extruder motor, which is plugged into a 12-volt power supply. And in order for this test to pass, the screw had to be spinning at a constant RPM, and filament had to be extruded out after it was melted. After the plastic was melted, filament had to be extruded out at a constant rate as to not have diameter or hollowness problems.
Now these are our data and collection results. The grinder test was a success. We were able to grind filament down to a 3 millimeter radius with a 94% efficiency. However, the heating test and the extruding test were not as successful. The heating band was not able to stay within a consistent 205 degrees Celsius because the temperature of the band increased and decreased too quickly for the temperature controller to keep up with. As a result, our extruding test also failed. Even though the extruding screw was able to turn at the proper torque and speed needed, we weren't able to extrude filament due to the safety issues with the heating device. So it ends up as a failure. Our final product was not able to extrude or melt or extrude filament. However, it grinded it very well. This is mostly due to the high temperature fluctuations within our heating band. And to resolve this, we would then incorporate a parallel resistor circuit within the heating device. This will limit the current going into the heating band, and which will lower the fluctuations in temperature. And here are our references.
Some solid ways to save money there, yeah? Okay, definitely look for that moving forward here, because we do a lot of 3D printing. So, all right, so our next group up is looking into heat exhaustion prevention, okay? And the members of that group is Laura Duffy, Dante Grilli, and Gregory Hazen. Come on out, guys.
Hi everyone, so my name is Laura.
I'm Dante.
And I'm Greg, and we'll be going over Zero Cool, our solution to heat exhaustion and heat stroke.
Okay, so our problem statement is that heat exhaustion is the third leading cause of death in high school athletics, and it was the leading cause of preventable death in 2007. And people need an affordable, convenient way to combat heat exhaustion while being active outside.
So this is our problem justification. We went down three main paths for this: health, legality, and economics. So on the health side of things, it's pretty obvious. People suffer from heat stroke and heat exhaustion, and it causes needless suffering and death. So it's the third leading cause of death in American high school athletics, and it's affected people that we all personally know. On the legal side of it, there have been many lawsuits that have resulted from people suffering from heat exhaustion. This comes from schools that have been sued for negligence on the part of coaches, for athletes that have overheated during practice, and other things like that. And then for the economic side, there's decreased productivity during the summer months when people get hot outside. States mandate that people take breaks if they're working out in fields, so this lowers the productivity of workers outside.
Okay, so our first step was looking into current methods related to our problem. So the first problem, or the first object that we found was the instant cooling shirt, which is a wicking fabric shirt. It has hyper freezing technology. And then we had the mission cooling towel, which is a towel when soaked, it becomes like a cooling wick fabric for the athlete to cool themselves off with. And then the Chillets cooling headband, which is basically has wicking fabric on it and has like an ice pack on the top so it can cool the user's head.
So we found several patents that all covered aspects of the product that we thought we wanted to create, but none of them fulfilled all of the requirements, which is how we determined that there was a gap in the market that a product that we made could fill. So for example, we found the strappable ice pack, which is pretty self-explanatory. It's just an ice pack that you can strap anywhere on your body, and it's refreezable. We also found a monitoring system that will monitor the air temperature, body temperature, humidity, and other things like that, and then it will alert the user if there are those conditions outside that would be unsafe for them to exercise in. And then we also found something similar to the ice pack that was a cooling vest that would go around the torso area, and it could also be refrozen for multiple uses. So we had four main disqualifying design specifications that would determine the success or failure of our product. So the first one was that the product must be able to keep a person cool during moderate to extreme physical activity, which we determined was jogging to running, for at least an hour. The second one was that the product must be able to tolerate temperatures of 64 degrees and above. The third was that the product must not exceed 5 pounds. And the fourth was that the product must not physically encumber or restrict the mobility of the user in any way. So we all came up with 2 to 3 initial sketches for our design concept. So both of mine were full body garments that could be worn by the user. One of them was more of a skeletal structure, and one of them was more of a bodysuit. They were both intended to be undergarments, and they both had not only active cooling, but a monitoring system that would alert the user of dangerous conditions.
So my two sketches differed from that. My first one I went for was more of like a shorts type of design, which used water and radiators to cool the user. with different pads on the upper legs to cool the areas that dissipate heat the best. And then my second one was a shirt with Peltier type devices. These separate, these turn one side of the device cold and one hot when a voltage applies across of it. And so this implemented a heatsink design that would dissipate heat into the air.
Okay, so my first two sketches, both were shirts and integrated cooling tubes through the arms and down the sides of the shirt. The first one on the left has cooling pads around the neck and then under the armpits and around the sides. And it has a cooling regulated device built into the shirt. And then the second one has a built-in fan in the center with a cooling regulated device on the bottom.
So after our first sketches, we shared all these designs with each other and came up with 3 final concepts.
So my first final sketch had the cooling tubes going down the arms and also had pants that also had cooling tubes and had cooling pads on the thighs and underarms and on the neck.
My final concept was the full bodysuit concept that I mentioned earlier. It was meant to be worn as an undergarment. It would be made with a breathable wicking fabric, and it would have that central alarm system that would alert the user of dangerous conditions. And it would also have removable cooling patches under the arms, and it would be customizable.
And then my final concept integrated a sensing unit, like the other two, on the arm to prevent overheating that would warn the user when they were getting too hot. It had the active cooling with the Peltier devices, breathable fabric that wicked away sweat. It was lightweight in order to not restrict mobility, and it covered the major areas of the body that dissipate heat the most, which is mainly the torso and like upper arms.
Okay, so for our decision matrix, we had our specifications up top, and then we graded each specification, each idea by specification based on weight, 1 through 5, and my idea ended up winning with 74 points.
So the first component of our product, it was split into 3, 1 for each of us, was the actual construction of the garment. So what I chose to do was, well, first I researched different fabrics that we could possibly use for the construction of our fabric, and I ended up choosing a polyester one after extensive research. And then I traced a pre-existing shirt, the seams of a pre-existing shirt, and created shirt patterns from that. And then I cut the patterns out in the fabric that we chose, and I actually used a combination of hand sewing and machine sewing to physically sew the shirt together. So the final design ended up being a just standard t-shirt in a US size large using that polyester material. It also has a zipper pocket on the left arm, I believe, that contains the electronic components. And there are also small sleeves at the front and back hem and on the shoulders that contain the cooling tubes. So for testing, I had 3 main tests that I performed on the shirt. The first one was a machine wash test, which was basically just putting the garment in a washing machine with a standard detergent to make sure that it could withstand, or the seams and the fabric could withstand a regular washing machine. The second one was a mobility test that would kind of test all of the extremities of the body on the shirt and make sure that none of them were compromised. The only one that was the left arm that had the electronic component on it, just because there was a slight amount of weight that was added. So that kind of added to the constraint of mobility. And then the third one was a weight test to make sure that the product was under the 5-pound limit. And it was, I think it was 1.682 pounds, so it was well under the 5-pound limit that we had set for ourselves.
Okay, so for the cooling component, I designed cooling tubes that had 20% saltwater solution inside the tubes for optimal length of cooling time for the user. And then in order to keep the cooling solution inside the tubes, I 3D printed custom cooling caps to attach to the ends of the tubes. And to prevent further leakage, I coated them in a liquid plastic. For the testing, I first did a temperature test, which I put the cooling device in a freezer overnight to see how cold it would get, and it ended up being negative 18 degrees Celsius. And then I did a cooling test, which was to test how long the device would stay cool, and it stayed cool for about 30 minutes. And then I did a leakage test which tested where I applied pressure to the tubes to see if water would still come out of the tubes, and we're currently working on a solution to combat that.
So I did the monitoring component. So step one was construction. So we implemented a humidity sensor, temperature probe, Arduino, SD card, battery, and screen into the device. The entire enclosure needed to be waterproof to ensure that rain and sweat wouldn't compromise it. All leads needed to be soldered and assembled inside of the component. And then software development in C and C++, it's a combination of C and C++ on the Arduino to actually monitor and display when there is a dangerous condition. So this is the final device. It's a 5.5 by 3.5 by 2-inch enclosure. It displays the current status to the user and lights up if there's a dangerous condition. It is removable from the shirt, so the shirt can be washed. And then there's a temperature probe that is placed under the arm through the shirt that monitors the internal body temperature of the user. So for testing, the enclosure was placed under running water, and it was dry inside after it was removed. So this makes sure that the electronics were not going to malfunction during use. All components are rated for use in 130 degrees Fahrenheit and above with 90% humidity. So this is well in excess of any realistic temperature that someone would work out in. And the data was successfully recovered from the SD card. So you can see the 3 columns have the timestamp, temperature, and humidity. And we use an algorithm on the temperature and humidity to determine if there's a dangerous condition and alert the user. So Zach?
We have a lovely model of our expert. Here he is. Yay for Zach.
Okay, so for our next steps, for the cooling subsystem, I would like to continue modifying the cooling tubes so that they can be more efficient so they don't leak as much. And I would like to do more various temperature tests to see how the cooling devices would perform in various temperatures.
So for the garment, some next steps would be to do an actual wear test for a longer period of time while the user is exercising with all of the steps combined, so having the cooling and the monitoring implements in them. And then just to continue to develop and improve the containment of the cooling tubes because they're a little loose as of right now.
And so for monitoring, we want to do a full-scale test with the user running to ensure that it adequately protects the electronics inside, determine how long the battery lasts on it, so we weren't able to do that due to time constraints. And then finally, work on making it smaller. Due to just the size of the electronics that we elected to put in the monitoring device, it turned out to be pretty big and bulky on the arm. So with future development, we could probably get that smaller. Thank you.
I may or may not be wearing one of those right now. Just take a look here. All right. So coming up next, okay, we have a project on transitional self-myofascial device. Yeah, this was the first time I ever learned about this or heard about this, and we'll bring out Atish Gupta and David Jackson to tell you about it.
All right, before we begin, I'd like to thank all of you for coming out tonight. We really appreciate your support. I'm Atish Gupta.
I'm David Jackson.
And this is our transitional SMR device. So before we get into it, I'll break down what we're going to be doing. So first, we're going to go through our justification for our problem. We're going to go over the prior solutions. We're going to go over the design for our prototype, the testing we conducted on it, the prototype itself, and then thoughts for any future development we might conduct.
So the problem we worked with relates to stress injuries in young athletes. Up around 50% of injuries reported by student athletes, at least documented at medical facilities, are a result of overuse, of which 25% or a quarter escalate into more serious injuries. Because with this project, we're taking an approach of designing a solution to this issue. We specifically worked with SMR tools, also known as self-myofascial release tools. These are tools like foam rollers, hand rollers. You'll commonly see them like around gyms that work to stimulate muscle flow, and in some cases, as we'll point out, workout knots, which sort of facilitate recovery of the athlete.
So in preparing to justify our problem, we reviewed multiple sources You can see some quotes from them up on the board. We also conducted interviews, personal interviews with experts in the field, such as Dave Welsh, owner of the Haddonfield Running Company, and Stephen Shackley, who's been coaching for several decades now. And what we were able to find from them and from the surveys we conducted with student athletes was that stretch injuries are a serious problem that many face, and that better steps need to be taken to solve.
So to sort of preface our brainstorming phase of, and concept development, we looked at prior solutions that were taken, I'll be starting with the foam roller. There's 2 devices that had the most influence on our project and sort of helped us identify this market gap of, there's sort of like a lack of general portability between the 2 products, as well as both products, both products sort of offer something that the other doesn't. With a foam roller, it's sort of large, clunky, not that portable, but because you use it by applying your body weight to it on the ground, the pressure's not adjustable, which makes it really effective for working out knots to help with recovery and injury prevention, but it has very limited range and doesn't work so well for certain other applications. But that's where the muscle roller stick is much better because it's a handheld tool. It has much better adjustability in terms of pressure applied, but because of and that allows a much better range, but because of that, it's much more effective as a warm-up tool than actually an injury prevention tool. This is the body stick, which is one of the most popular models on the market. You'll see that it's sort of a rod with a lot of spindles on it that can sort of wrap around areas, which gives it much better range than the foam roller.
So when we were developing the design constraints for our product, the primary thing we wanted to do was combine the best aspects of both of the designs that you just saw. So we wanted it to be able to massage all the same muscle groups, and as David said, target knots specifically with adjustable pressure. So what we decided on was creating a transitional SMR device. So some additional design constraints we had was that it should be able to sustain up to 250 pounds of weight, and just overall implement the durability and versatility of both tools to create a better product.
So these are some of our initial sketches. In the top right, we have a concept for a fold-up foam roller, which wouldn't really offer the benefits of a muscle roller stick, but would still be portable with that. And then we took a sort of spindle expansion approach in the bottom center. Up on the top left is comparable to what we ended up going with, which was just a uniform expansion across the entire device. These are some of the initial locking concepts that that is helpful. Some of the initial locking concepts that we went with. So we have here, there's sort of, there's 2 telescoping axles basically, and then so pressing a button, So pressing a button on the interior of the axle would cause the orange piece here to slide. These outer arms would be essentially pulled in by pressing a button, allowing the axles to slide across each other, and so thus allowing the device to transition between the 2 different modes that it can go between.
So this is the 3D model that we created. So this is the expansion apparatus in its final form. And this is the design we went with for our prototype. So we created this 3D model as a proof of concept. And the final prototype ended up looking very similar to this. This is the locking mechanism as David just discussed. And this is
this is just a diagram that shows how this is integrated in with the handle on the left. The center, there's sort of an outline in the bottom center that would be the exterior of the axle, and so pressing the button, you'd be working against a spring that does the work in the center for you.
So this is the next 3 slides are the images of the stress testing that we conducted. So in the fully expanded version of the foam roller option, we wanted it to be able to sustain 250 pounds of weight. So in order to do this, we had to determine what the optimal configuration was. So we 3D modeled the structure, and then we applied 250 pounds in the software and measured the resulting von Mises stress and deformation. So on the left, you can see the von Mises stress, on the right, the deformation. So you can see that the one with the right angles was the optimal design because the next ones exhibited higher von Mises stress and deformation. So this is, in the end, the format that we chose for the foam roller. We also conducted testing on the materials. So what you're seeing here is the deformation due to 250 pounds of weight on the low density ethylene plastic. And this is the deformation due to the high density ethylene plastic. So based on this, we were able to determine the Young's modulus and elasticity of the plastic that we would use in the final product. We also conducted testing on the foam that we were going to use. So we ordered foam from a company called Smooth On, and we poured it into molds and created samples. And on these samples, we conducted compressibility tests. So we applied a given amount of weight to it and then observed the compression, and then we calculated the percent compression per weight and then compared it to industry standard foam rollers. And these are the results that we obtained. So as you can see, both of the foams that we did order ended up being too far off the mark for us to use them in our prototype, or not even thinking about using it in our final product. But the important thing was that we were able to determine the percent compression per pound of the industry standard, which is what we would want to replicate.
These are some of the initial prints from prototyping, and then the internal mechanism on the right is sort of those parts put together.
And this is the final prototype. Well, it's not the final. It's an initial prototype of the expansion mechanism. And it's very rudimentary, but we decided it was extremely instrumental in us determining what the product should actually look like, and very essential to knowing what we should do when we're going on with further work.
Yeah, so with the prototype that we ended up finishing with, we sort of established our concept that we wanted to work with. Moving forward, we would want to go through further iterations in prototyping. We'd want to make the extension arms a little bit shorter because obviously it sort of came out much longer, but that was just because we were working with the 3D printer. It was sort of important to make those arms long enough that we could effectively work with them. We would need to integrate an axle that works with the bearings of the external mechanism that we currently have right now, and then sort of integrate all the internal mechanisms and the handle with the outer exterior expansion mechanism. We would then have to move in, well, also kind of aesthetics, because right now the cuts for the...
It kind of looks like a giant spider.
Yeah. Then we would probably want to put together a focus group or something of the like to test the performance of the tool and make sure it sort of holds up mechanical functionality after basic use and stresses that a young athlete would exert on it.
Yeah. Thank you for your time.
All right, so our next group up here they are looking at opioids and the epidemic surrounding them currently, and they developed a product called the Pill Keeper. So let's bring out Allison English and Orly Smith for that.
Hi, thank you for coming out here, and thank you for listening, since I know you're all getting tired probably. I'm Orly Smith.
And I'm Allison English. And our product is called Pill Keeper, Preventing Prescription Opioid Addiction in the United States.
So in the United States and in the world in general, right now, we're in the midst of an opioid crisis. A large percentage of patients that are prescribed opioids take more than their instructed amount. Sometimes after a medical procedure, pain gets to be too much, and the solution seems to be taking more pills. This often results in an opioid addiction. As of 2018, approximately 2 million people living in the US are addicted to prescription opioids. This amount of addiction can be linked directly to a cause, which is access, too much access to their pills. Our goal was to create a product that limits a patient's access to their pills so that they can't take too many and get addicted.
So we used several methods to justify this problem. The first was we did research, and we found information such as there have been over 165,000 deaths related to prescription opioid overdose from 1999 to 2014. And also about 80% of the current heroin addicts started on prescription pills. We also did an interview with Dr. Basson and her team of addiction specialists at Cooper Hospital, and we took a survey of doctors who are also good with addiction or have studied addiction. And we have asked them a few questions, but most significantly if they know some sort of product that could help prevent addiction. And so far they have all said no or some form of medication, but that's not our goal. So our conclusion is that opioid addiction is a problem.
So we started by researching some other solutions, and we really didn't find many. The first one that we found was the Sarasota pill dispenser. It's not patented or anything, but it's mostly conceptual, but it's basically a circular product with a dial inside that holds your medicine, and a timer counts down until you can take it. It's easy to use, it's lightweight, and it's easy to transport. But one of the main cons is that it's very easy to break, and also it can't prevent abuse, but it alerts doctors after you've already broken it and taken all of your medicine.
So another device we found was the MedMinder pill dispenser. It is also very easy to use, and it locks well, so it does prevent people from taking medication when they're not supposed to, and it uses a timer. However, it is very expensive. It would be hard for the average person to get it. It's difficult to transport, it's heavy, it needs to be plugged in at least some of the time, and it's kind of inconvenient for people who need opioids because they're typically having them multiple times a day. So if someone needs them every 4 hours, this device is more for pills once a day, so it's not that useful in this situation. So we found that we need some sort of device that is hard to break but also transportable. So we came up with a list of specifications, and these are a list of criteria and their importance to us, and we use these to form our constraints to help us design the product.
So our list of constraints consists of 11 things, but one of them was that it should be able to fit within about a 6-inch square and weigh less than a pound. It should cost $20 or lower for people who are buying it. It should hold at least 63 doses. So that means if you're taking a week's worth of pills and you're taking 9 pills a day, which is a lot of pills, but we wanted to include anyone's prescriptions amount. It also has to be difficult to break. It has to be easy for the patient to access their medication when they need it, like when their time counts down on the clock. And the dosage schedule has to be adjustable. So here are our final designs. These are mine. The key points of this final design were that it was a circular device with a conveyor belt dial type thing inside of it that holds the pills and turns. There's a timer on the outside that counts down, and once the timer hits 0, the internal part turns and dispenses a pill for you to take.
This is my design, and the most significant part of my design that we used later was a form of security so that people who aren't prescribed the opioids can't take someone else's, and also some form of communication with the user, so if they can't take their medicine, they know why.
So a lot of our decisions were made using decision matrices over the course of our product development, and this was our second main one and our final one. We made a list of criteria based on our constraints and specifications and weighted them based on how important they were. And then we held up Ali and I's final designs against the weights and calculated the final scores. And they were very close. Mine ended up being slightly more, so our final product looks more like my design, but it incorporates both of our points from our final concept designs.
So this is a sketch of our final design. This is before our critical design review, so when we had a panel look at our design and give us suggestions. So some of the changes from this design and our final design is there is no door. We decided that it wasn't necessary and the pill slot wasn't large enough for a door to be necessary. Instead of opening on the bottom, it opens on the top. Instead of using LEDs, we decided to use a display. And instead of using a fingerprint scanner, because we learned that would be way too difficult, we incorporated security switches.
So this was our final materials list for our product. Included a Raspberry Pi, stepper motor, a button, a display, lots of printer filament, a stepper motor hat, lots of wires, and various switches. So these were part of, I did the AutoCAD design and the hardware part of the project. So this was my AutoCAD Inventor design for the lid and for the attachment for the stepper motor. This was one of the assemblies I did. It's the bottom piece of the product, and it has the dial that holds the pills in it and also the stepper motor attachment. And one picture just shows you the planes that are used in the design. This was another assembly, includes the top part of the container. So you can see that it attaches together, the pieces attach together so that you can take them apart, remove the dial, remove the stepper motor, replace medication, and preferably this would only be done by a pharmacist. This was the final overall hardware. So you can see that the stepper motor is sitting inside of the stepper motor attachment, and that is attached to the dial, and the top of the container is attached to the bottom piece. You can see that there's a hole in the side for where the dial can be dispensed, and there are slits in the side of the dial that line up with that hole. So you can just tilt it slightly and it'll come out.
So I was in charge of the electronics and the coding. So this is all of our electronic equipment, and just starting at the top and going clockwise, we have the stepper motor hat, which allowed us to connect the stepper motor to the Raspberry Pi. We have the Raspberry Pi, which is the computer we used. We have our security switches. Our final product will have 5, but for this prototype we have 3 for demonstrative purposes. We have our button, which you use to turn the dial when the time is right. We have the power supply for the stepper motor, the power supply for the Raspberry Pi, the stepper motor itself, which is used to turn the dial, and our display, which is to communicate with the user. So we had 4 main messages that could be displayed on the display. The first 2 are if the security is fine. So it tells you if you have waited long enough between doses. So the pharmacist will set a time, and if that time has elapsed and you press the button, then this message will be displayed, and it'll tell you how long it's been since your last dose, and the stepper motor will turn the dial so the next dose is available. However, if not enough time has passed, then the other message will be seen, which is too soon, need to wait, and then how many seconds are left or minutes. We did everything in seconds currently to make testing faster and easier, but our actual product would be in minutes and hours. So we also have this set of security switches, which we've said is to prevent the wrong person from taking the medication. So how these would work is at the pharmacy, each person would be assigned a code for their switches. And if the code is wrong, then they cannot access the medication. The stepper will not turn the dial even if enough time has elapsed. So if you press the button and the security code is wrong, the first message you get is just wrong code. However, if you continue to do that, we have a punishment system, because if someone wants to just keep trying combinations until they get it right, that would be a problem. So what we've done is we've incorporated a weighting system, which the iPhone has done too, for locking if someone keeps trying to put in the wrong password. So what happens is if someone hits the button and they're wrong, they have to wait 2 to the n seconds. Again, in the actual device, it'll be longer than that, but for testing purposes, this was faster. And then n is equal to how many times they've gotten the code wrong. We currently have a max waiting time of 2 to the 6, so it can't get higher than that even if they continue to get it wrong, because if someone, like a toddler, takes it and they just keep pressing the button, then the medication might become unavailable and it's not their fault, and you don't want them to have to wait 10 years in order to access their medication.
So the testing for our device was performance-based. We basically just put our components together and see if they worked as we hoped they would function. Some of our testing involved measuring size and weight and timing of how long it took to use our product, and also testing the durability of it. That included dropping it to see if it would break. Testing results, the product was successful, and it did what our ultimate goal was, but it would be better if it were smaller and stronger.
So here's a video. So here's the button being pressed and the dial turning. Here's it being pressed and not turning because not enough time has elapsed. Now enough time has elapsed. Now here are the security switches. The combination is currently right. Now it's wrong. You press the button, and it says wrong code. You press it again, there's a wait time. You still have to wait, increase the wait time. And then once the security switches, the combination is correct, and you wait out the wait time, then the stepper motor turns again.
So did our final product fulfill our constraints? It was able to fit within a 6-inch square and weigh less than a pound. It did end up costing more than we thought it would, but we don't know how much it would cost if it was being sold. It was able to hold at least 63 doses, and that was one of our most important constraints. It wasn't incredibly difficult to break, but part of our original goal was to incorporate metal into the product also, and we did not have enough time for that.
So we did succeed in making the dosage schedule be adjustable. However, it is not easy to do because currently you have to go into the program to do it. And our goal at the beginning was to create some sort of interactive website so it's easy for the pharmacy to change things in the device, like the dosage schedule, but currently we did not have enough time to accomplish that. It must also be easy for the pharmacist to access the medication. We haven't succeeded with that yet because currently the electronics are all on top of the dial, which means they all have to be removed in order to access the dial. This is a problem, but if we had more time, we could probably create a place for them to fit so you could just take them all out at once to make it easier, but we did not have enough time. However, the product is very easy to use. It's easy to access the medication in less than a minute. You just press the button. If the security switch is wrong, you just turn the switches, and that's very quick and easy. And we think the product is aesthetically pleasing.
So if we had more time, we would, like I said, we would have made it more durable. So this means adding metal. Originally, I wanted to make the product metal-based and then coat it in plastic, so that would be the aesthetically pleasing part, but we ran out of time for that. Also to make the lid fit more accurately, hopefully make it smaller. It's bigger than it fits within our size constraints, but it's bigger than we thought it would be because the electronic components ended up being bigger than we thought they would. And we also would like to create a website and an app for people to use and a way for pharmacists to interact with it quicker and faster, and a way for people to understand better how much medicine they have and how their product works and how it's relating to their health care.
So thank you for coming, and we hope to see you at the poster session.
All right, so this brings us to our last presentation of the evening. We have the Cold Shield coming out, and the people leading that charge are Mark Ebner, Alex Kupp, and Shweta Nair.
My name is Alex.
I'm Mark.
I'm Shweta.
And the problem we're trying to solve is eliminating the effects of the cold on manual dexterity. The idea for this problem came to me from my own experiences performing in the marching band. As we got later in the season, it began to get colder outside, and I noticed that I wasn't able to play to the same capacity that I had been earlier in the season. I realized that that was because my hands could not move as fast as they had previously in the season when it was warmer outside. And we connected the cold to a lack of dexterity. And that's the problem that we're trying to solve for both marching band members and for athletes.
The problem statement that we used for this project was that in cold environments, even as mild as 52 degrees Fahrenheit, researchers have reported a 50% decrease in hand dexterity and a 70% decrease in finger dexterity when gloves are worn compared to bare hand performance. Primarily, this negatively impacts marching band members and athletes who continue to practice and compete late into the fall and winter.
So next, we had to justify this problem, and in order to do so, we found a target market and figured out if they experienced the same problem with cold weather decreasing their manual dexterity. So we surveyed marching band members and baseball players, and at a survey of over 100 people, we found out that 62.3% of people surveyed said that yes, this product like this would help them and it would benefit them in their activities, and only 8.2% said no. A list of other outdoor activities that would help this, that would benefit this is plumbers, electricians, and other activities. As of now, the products on the market are centered around bulky gloves that are meant for like snow and shovel use and aren't great for manual dexterity. And our goal is to solve the problem of decreasing the manual dexterity and keeping the hands warm. So here are some current methods or actions that are currently in use, and like I said earlier, are primarily used with like a lot of bulk in the gloves. Solution A, as you can see, is a normal glove, and it has a lot of bulk on it, and it did do well in insulating the hand, and we use that in our product with how we picked our materials for the glove. Solution D on the top right is another bulky glove, and this glove featured a battery pack on the back of the hand, which we use in our product, and helps us, power it, and is easily accessible because of its access on the back of the hand. And solution F, we didn't use any of their aspects of the product in our own, but this was a pouch put around the waist that would keep your hands warm for a time, and then you'd have to take them out for your activity, so this wasn't ideal for us.
After researching the problem, we then came up with a list of constraints or specifications that we would then use to help direct the ideas for our prototype and product. So the first two on the list have to do with keeping the temperature in an ideal range. So obviously if the glove gets too hot, that could actually put the user at risk of burning their hand. So the product has to remain under 105 degrees Fahrenheit, which keeps the user safe. Additionally, for the product to actually be useful, the heat has to heat up to a certain degree, which we determined to be room temperature, in order to keep the hand from losing dexterity. As Mark was saying, some of the products that we saw had a lot of insulation on them, which ended up affecting the dexterity themselves. So our product, because we're trying to do better, it cannot in and of itself affect the dexterity of the product. And one specific idea with that is that the product cannot weigh more than 300 grams. Additionally, the product material must be waterproof and snowproof. Later in the season, it can rain or it can be snowing, and we want to make sure that the product and the electronics inside remain safe. And any substances, such as the batteries, have to be easily disposable and not affect the environment.
So after setting these design requirements, we each came up with our own sketches and our own ideas. They were all based around the same concept with a fingerless glove, battery pack on the back, and wires going throughout that would heat the hand. Going from left to right, there are Shweta's, mine, and Alex's sketches. And from that, we started the construction of the product.
Our initial testing included using the Logger Pro temperature program to test the wire that we chose to be 60 centimeters long with 3 AA batteries connected to it. What we did was we placed the temperature probe, we placed a wire around the temperature probe and ran the Logger Pro program, and we ran some graphs to see how far the temperature would go. We also connected this wire to our glove and connected the temperature probe to that to see how far the temperature would go there. And we also took a water test for both our inner and outer layers of the glove. The inner layer was polyester and the outer layer was nylon. For this test, we put a piece of paper or a napkin inside each of these gloves and dropped a little bit of water onto each of the gloves. If the paper got wet, that meant the test failed, and if the paper did not get wet, the test was a success. The analysis of the test. was that for the water test, the outer layer was water resistant because there was no water on the paper we put inside it, and the inner layer was not water resistant because the paper got wet. This is insignificant because the inner layer will not be exposed. As for the heat tests, we did 6 Logger Pro tests with varying parameters, 32 centimeter wire and 60 centimeter wire, and we realized that the ideal parameters was that the length of the wire should be 60 centimeters, the voltage should be 4.9 volts, which was equivalent to 3 AA batteries, and the resistance should be 3.1 ohms.
While constructing the prototype, there were 2 main parts of it. The first part was creating the circuit. The circuit consists of a battery pack, a switch, wires, and the heating element itself. The heating element is made out of stainless steel wire. The way the circuit works is that as current travels through the heating element, the resistance in the heating element causes there to be some friction and energy loss. That energy loss is heat, or thermal energy, which is what our product is trying to do. While constructing it, what we did was we soldered the different parts together. On the battery pack, we also mounted a small bit of a circuit board which aided us in doing this, and that's where we put the switch. We then hot glued that to the battery pack. The second part of building our product was the 2 gloves. As we said, there's a bottom layer and there's an upper layer, and these 2 layers, A, allow us to put the wires in between them, and B, allow for more insulation. To put these 2 gloves together, we did a lot of hand sewing, mostly done by Shweta. We sewed the battery pack onto the inner glove. We sewed the 2 gloves together at the fingertips and at the bottom, or around here. And then we sewed a strap onto the inner glove, which protected the batteries.
So the prototype, which is around my hand right now, includes a switch that turns the glove on and off for the heat to go through the wires that are placed between the layers of the gloves in a fashion that's around the fingers, so that the heat dissipates through the hand and into the fingers. The top layer of the glove is sewn to the bottom layer of the glove at the fingers and at the bottom of the glove, and there's a strap covering the battery pack, which is also sewn to the bottom of the glove, and this strap is sewn onto the battery pack itself and the second layer of the glove. For our final prototype testing, we did another temperature probe test with the Logger Pro program, except this time we did it with the full prototype. We stuck the probe inside of this prototype, both the layers of the glove, and we ran a graph with both heating and cooling. The red line is heating, the blue line is cooling. The cooling is a shorter line, but the trend is the same. It goes down in the same amount of time, and it takes, we measured the amount of time it took to heat where it bottomed out. As you can see, it kind of bottoms out around 1,300 seconds, and the analysis of these tests showed that the max temperature was 39.1 degrees Celsius, which is equivalent to 102.38 degrees Fahrenheit. This met our constraint to be less than 105 degrees Fahrenheit, which was perfect. The time it took to get there was 1,280.5 seconds, which is about 21 minutes, which is not too much time for the user to be able to get warm as he needs. And the constant temperature that it stayed at, that it bottomed out at, was 37.9 degrees Celsius, which is almost exactly 100 degrees Fahrenheit, which is also perfect because it is very near to internal body temperature, which is what we were going for, right above room temperature. Thank you for your time.
All right, thank you all. And thank you to all of our students for your excellent presentations here tonight. They were amazing. You guys did a great job. On that note, students, okay, take a moment to think about what you've done this year. A lot of hard work, but think about the benefits of your work. You may recall, I stand in the hallway usually to walk you in the classroom. And usually when I walk into the classroom, I say, let's save the world. Yeah, you guys all know that's true. I say that. Kind of like what a hero would be doing, go save the world. You may have thought, and I'm judging this as true, that this is just another joke from me, okay? But as you can see, the meaning of what that is kind of what you did tonight. All of your projects have hero-like characteristics in that they improve and protect someone's quality of life. Just think about what your product can do if it's taken to market and released on a large scale. Society and mankind alone benefit from your ideas, talents, and now your superpowers. You may not get the spotlight like the heroes we see on the movies, but the ideas you presented on this big screen are no less important. There are a lot of heroes in the world who are capable of improving the way we live, and you are all ready to contribute. So congratulations on a job well done this year. Excellent job. At this time, I would like to invite our Cherokee principal, Mrs. Charlesworth, Board of Education members, Barry Fitzgerald and Bonnie Olt, and the Supervisor of Technology Education, Michael Carr, to the stage to present the chords. As we present each student with their chord, I'll also indicate whether a student has been awarded extra recognition from the College Board as an AP PLTW student. This recognition demonstrates to colleges and employers that the student is ready for advanced coursework and interested in careers in this discipline. To earn recognition, the student must complete 3 courses in the pathway, 1 AP course, 1 PLTW course, and a 3rd course, either AP or PLTW, and earn a qualifying score of 3 or higher on the AP exams and a score proficient or higher on the PLTW end of course assessment. So as you're called up, I'll also recognize you for that. All right? So our first student tonight is Laura Duffy. Laura received AP PLTW recognition. Next up is Paul Durante. Mark Ebner, who also received AP PLTW recognition. Allison English. Lauren Fowler. Dante Grilly. Atish Gupta, who received AP PLTW recognition. Gregory Hazen, who also received AP PLTW recognition. David Jackson. Palak Jain, who also received PLTW AP recognition. Alex Kopp. Michael Kurtz. Nicholas Mascolo, who also received AP PLTW recognition. Kiefer Montanaro. Shweta Nair. Harrison Olt, an AP PLTW recognition. Andrew Palmer. And Orly Smith. Let's have one more round of applause for our class of 2019. All right. Thank you, guys.
All right, one more special presentation. As we've said, this evening is about our students, and the students this evening would like to make a special presentation, so I'm going to call up Orly Smith and Harrison Olt.
All right, so we'd like to bring Mr. Knaus on stage again. Mr. Knaus, I want to thank you on behalf of all the students in our class. Despite the countless hours of complaining, Mr. Knaus was always our biggest supporter, our most helpful mentor, and our biggest fan. He genuinely wants the best for all of us, and he invested the time to not only make us better engineers, but better people. After 3 years of seeing your face every day, this will be a tough goodbye, but we're finally ready to take on the world that you've prepared us for.
So as a class, we got you a little gift just so that you can see, I hope you can see this just from us, but how much you mean to us. So.
Thank you. We'll be good.
Thank you.
Oh, should I open it now? Yeah. At least take one of them. All right, so this is interesting. So I have electronic kind of, I have one electronic kind of stuffed animal. So we got an LED here. There's a few things in here. It looks like a resistor. So we can, now we have a series circuit. So that's exciting. All right, cool. Thank you, guys. Thank you.
Thank you. And in closing, I would like to thank the Lenape Regional High School District Board of Education, our Vice President, Mr. Barry Fitzgerald, and Mrs. Bonnie Olt from Evesham Township, who assisted us this evening with handing out our cords, our Superintendent, Dr. Birnbaum, the Director of Curriculum and Instruction, Mrs. Zanakis, all of our district administrators, our principal, Mrs. Charlesworth, my fellow administrators, the entire Cherokee High School faculty, all of our outside volunteer engineers, and our Project Lead the Way teachers for their support, commitment, time, and dedication to our students. I would also like to recognize all of the parents, guardians, family, and friends that have come out to support our students this evening and throughout their journey in the Project Lead the Way program. To our PLTW teachers, thank you for leading, facilitating, and teaching our students. This evening is about our students. This group of students began a journey 4 short years ago as the inaugural group of Project Lead the Way students at Cherokee High School. The countless hours of work, both inside and outside the classroom, were evident by these extraordinary projects that were presented this evening. This is a culmination of your efforts. You have set the standard for the PLTW program at Cherokee and for those students that will follow in your path. As an educator, observing your enthusiasm, creativity, and knowledge excite me to see where your path to success will lead you and the brilliant things you will accomplish in the next phase of your lives. The cords you received tonight should be worn and displayed proudly as a symbol of accomplishment at your graduation ceremony next Monday evening. These cords will recognize your successful completion of the Cherokee High School Project Lead the Way program. We wish you all of the best in your future endeavors. In closing, I would like to invite all of our friends, family, and guests out to the lobby of the PAC to participate in a poster session where you'll be able to view and discuss the projects that were presented tonight with our students. Thank you. Have a good evening.